Good afternoon. Now, today we'll see last part of this chapter, that is nothing but different types of cameras, digital cameras or whatever cameras are available. Then we'll see their specifications, and then we'll see how to select the camera. Therefore, this first camera is CCD camera, means charge coupled device, that means digital camera. Therefore, you are observing the figures. This is interline transfer CCD. Interline transfer means what? If you are observing the diagram, different arrows are there. One arrow is moving from one line to other line. Therefore, that is nothing but interline transfer CCD, means charge coupled device. These are the vertical shift registers. These white lines are vertical shift registers. And these green blocks you are observing, they are nothing but active pixels. And this blue color rectangular shapes you are observing, that is nothing but transfer register. Therefore, this interline transfer, and then afterwards output is there. And then next is frame transfer CCD. Frame transfer CCD means what? Or whatever the data is there, that is transferred from one frame to other frame. See that entire frame transferred to the frame store. Whatever this frame is there of green color, whatever information is stored, therefore entire information is transferred to this another frame, and then this another frame is coupled to this light green color rectangles, and then you can take the output. Therefore, first of all, I will see the theory and then we'll see the video. Charge coupled device, CCD, it is known as digital camera. CCD consists of millions of pixels. As these pixels are exposed to the incoming light, these pixels will convert the incoming light into a charge, and the charge will get accumulated in these pixels. Once the charge is getting collected by these pixels, these charges are being transferred using this horizontal shift register, and these charges are being transferred into the vertical shift register. In this shift register, one by one, each charge is converted into voltage, and after the voltage conversion, each voltage is being amplified using the amplifier. Once the vertical shift register gets emptied, the same procedure is followed for the remaining charge, and one by one, each charge is getting converted into voltage, and after that, it is being amplified. Once the charge of each pixel is converted into voltage and amplified, the output signal is being converted into the digital form using the analog to digital converter. In this way, one by one, the charge of each pixel is getting converted into voltage. And the same procedure is repeated for the next frame. So this is the basic principle of the charge coupled device. Now we'll see this video, then you will understand. See that whatever that information is there, how that data is transferred from one rectangle, means one bottle to another bottle, like, or one glass to another glass, and at last output is there and it is connected to the buckets of photons. Okay, we will see another video.
CCD is the acronym for charge coupled device. It is a circuit which consists of light sensitive elements and it captures and stores the image in the form of electrical charge. These electrical charges are then shifted inside the device and it is manipulated by this device. It is based on metal oxide semiconductor. So next we'll see the working analogy of CCD. The working of charge coupled device can be understood clearly by rainwater analogy. The cups are spread over the rectangular conveyor belt, and after the cups are filled by the rainwater, it is transferred from the cups in the vertical conveyor belt and then to the cups in the horizontal belt. From the horizontal conveyor belt, the rainwater is shifted to the final storage container. In the same way, cells are collected in the photosensitive area and it is transferred vertically and horizontally by shift registers. Finally, it is transferred to the last capacitor and it is amplified, digitized and saved in the memory. Next, we'll see the architecture of CCDs. There are three types. First type is full frame. Full area is active in full frame and it is used to collect the light. To read out the data, a mechanical or camera shutter is used. The drawback in this type is image streaking. The next type is frame transfer. So here only half of the area is exposed to the incident light, which is image store area, and half of the area is covered with opaque glass, which is the frame store area. The image is transferred very quickly from image store area to frame area store, and no shutter is required and no image streaking. The third type is interline. In this type, alternate columns are masked and used for frame store. So the shutter time is very less and the image streaking is totally eliminated. But the cost is high to manufacture this type of complex architecture. Next, we'll see the working of CCD. So first, the pixels are collected and it is transferred and shifted by transfer gates and shift register. And finally, it is stored in the output capacitor and then it is digitized and displayed. And there are two main regions. One is photoactive region and the other one is transmission region. So let's see what is photoactive region. The photoactive region is an epitaxial layer of silicon. It consists of an array of capacitors. The image is projected onto this photoactive region through the lens. The electric charge proportional to the light intensity of the image at that location is accumulated in the array of capacitors. Next, transmission region. The accumulated charge in the photoactive region is then transferred to a shift registers by transfer gates. After that, by horizontal and vertical shift registers, the charge is transferred to the last capacitor, which is the storage capacitor. And from the last capacitor, it is transferred to the amplifier where the current is converted in images are smaller in size, consumes less power, and works at low voltage, low noise, and high sensitivity. Very faint and bright targets can also be measured. No chemical processing is needed. Next is disadvantages. Slower readout, no direct access to the pixels since it is read out serially. The applications are, it is used in astronomy for imaging, photometry, and spectroscopy. It is used in digital photography. It converts captured light into digital data. It is used in image sensors, signal processing, and in medical fluoroscopy. So thank you for watching. If you like the video, please like, share, and subscribe.
Next video we'll see.
You have 10 minutes to finish your research. Rush into searching on Google and you find a title that sounds credible. Click to the page and start reading with all your attention. By the time you read through the entire thing.
Of course, today's telescopes no longer use photographic plates. Instead, a charge-coupled device, or CCD for short, is used. These enable direct connections between an object's incoming photons and its image on a computer. Here's how they work. CCDs are based on a principle called the photoelectric effect. If a photon with sufficient energy hits an electron in the outer shell of an atom, the transfer of energy to the electron can be enough to free it from the atom altogether. This is a fundamental component of quantum mechanics, first analyzed by Albert Einstein in 1905. CCDs use a thin wafer of silicon to produce electrons from photons because silicon easily releases electrons with visible light. A tiny positively charged capacitor is attached to the silicon wafer in order to collect the free electrons. If we get one electron for each photon in the range, we'd have 100% quantum efficiency. The highest quality CCDs can achieve up to 90% quantum efficiency. It's interesting to note that the quantum efficiency of the human eyes, rods, and cones is only 1%. The photons start producing electrons as soon as the shutter is open. The capacitor collects the free electrons until the shutter is closed. At that, the voltage across the capacitor represents the number of electrons the capacitor collected. This information is sent to the computer. All of this is miniaturized into an integrated circuit and represents one pixel. CCDs are made of thousands or even millions of these configured as an array. The CCD on Hubble's Wide Field Camera 2 has 2K by 4K arrays for an 8 megapixel CCD. And as before, for color, we simply repeat observations with filters. For example, here's Hubble's photograph of the planetary nebula MYCN18, 8,000 light years away. This picture has been composed from 3 separate images taken with a blue filter to identify light from oxygen, and a green filter to identify light from hydrogen, and a red filter to identify light from nitrogen.
Okay, now we'll see next. Camera sensors, CMOS, that is complementary metal oxide semiconductor. Now see this. This is the active amplifier. This is a sampling capacitor. This is the active pixel area. Then this is just one block they have taken. Similar different types of blocks are there. Then this information is fed here, and it will go to the different blocks, that is photodiodes. These are known as photodiodes, pixels. The CMOS on chip analog to digital converter. Then whatever image is there in analog form, which is converted into digital form. CMOS complementary metal oxide semiconductor. In the case of the CMOS sensor, the fabrication technology is similar to the fabrication technology of the integrated circuits. Because of that, many peripheral circuits can be integrated inside a single chip. In the case of the CMOS sensor, the charge to voltage conversion as well as the voltage amplification is carried out in the pixel itself. So the processing speed of the CMOS sensor will be much higher than the CCD sensor. In the case of the CMOS sensor, the voltage that is generated by each pixel is being read in a line by line fashion. First of all, the first row of the pixel is being activated using this pixel select switch. This pixel select switch connects the output voltage of this pixel to the column line, and by activating the column select switch, one by one, we can read the data of each pixel, and the same procedure is repeated for the remaining lines. So in this way, in the case of the CMOS sensor, the data is being read in the line by line fashion. This is the overview of how CMO sensor works. Therefore, we will see this video, then you will understand.
Last 4 years, I have made over 40 crores. Now, of course, there have been lots. Those are a lot of things. I'm here to shoot a video from my home. And life was not like this.
Hey friends, welcome to the YouTube channel All About Electronics. So in this video, we will learn about the different image sensors which are used in digital cameras and the modern day smartphones. So we will also learn how this image sensor works, and at the end we will compare these image sensors in terms of the different aspects. So two types of imaging sensors which are quite commonly used in the imaging are CCD, which is the charge coupled device, and the CMOS, that is complementary metal oxide semiconductor. So both the type of sensor consist of millions of photosites or pixels. So these photosites converts the incoming light into the charge or electron. So although these two sensors are quite different, but they are common in many aspects. So these are the following steps which is being followed in both the sensors. So this sensor, first of all, convert the incoming light into the charge. So the photosites or the pixels are exposed to the light for a certain amount of time. And during this time, the charge will get collected in these pixels. So once the charge is being collected by this pixel, this charge is transferred for the further processing. And after transfer, this charge is converted into the voltage. And this voltage is being amplified using the amplifiers. So these are the common steps which you see in both the sensors. But depending upon the sensor, the sequence might vary. So now let us first of all understand how this charge coupled device or CCD works. So as I said earlier, this CCD consists of millions of pixels. So as these pixels are exposed to the incoming light, these pixels will convert the incoming light into the charge. The charge will get accumulated in these pixels. So once the charge is getting collected by these pixels, this charge is being transferred using this horizontal shift register, and this charge is being transferred into the vertical shift register. So in this shift register, one by one, each charge is being converted into the voltage, and after the voltage conversion, each voltage is being amplified using the amplifier. So once the vertical shift register gets emptied, the same procedure is followed for the remaining charge, and one by one, each charge is getting converted into the voltage, and after that, it is being amplified. So once the charge of each pixel is converted into the voltage and amplified, the output signal is being converted into the digital form using the analog to digital converter. So in this way, one by one, the charge of each pixel is getting converted into the voltage. The same procedure is repeated for the next frame. So this is the basic principle of the charge coupled device. Now let us similarly see how this CMOS sensor works. So in case of the CMOS sensor, the fabrication technology is very similar to the fabrication technology of the integrated circuits. So because of that, many peripheral circuits can be integrated inside the single chip. So in case of the CMOS sensor, the charge to voltage conversion as well as the voltage amplification is carried out in the pixel itself. And as the charge to voltage conversion and the amplification is carried out in the pixel itself, so the processing speed of the CMOS sensor will be much higher than the CCD sensors. So in case of the CMOS sensor, the voltage that is generated by each pixel is being read in a line by line fashion. So first of all, the first row of the pixel is being activated using this pixel select switch. So this pixel select switch connects this output voltage of this pixel to the column line. And by activating the column select switch one by one, we can read the data of each pixel, and the same procedure is repeated for the remaining lines. So in this way, in case of the CMOS sensor, the data is being read in a line by line fashion. So this is the overview of how CMOS sensor works. So now as we have understood how this CCD and the CMOS sensor works, now let us compare these two technologies. So first, let us compare these two sensors in terms of the system integration. So this charge coupled device or the CCD is very old technology. So in this technology, it is not possible to integrate the peripheral components like timers and ADC into the main sensor. So for these peripheral circuits, you will require the additional chip. So the overall size of the CCD sensor will get large. While in case of the CMOS sensor, as the fabrication procedure is very similar to the fabrication procedure of the integrated circuit, it is possible to integrate these peripheral components into the single chip. So in case of the CMOS sensor, it is possible to have a camera on chip or a system on chip. And because of that, the CMOS sensor is quite powerful. Now let us compare these two sensors in terms of this power consumption. So in case of this CCD sensor, we require the different types of power supplies for the different timing clocks. And not only that, the typical voltages which is being required for the CCD is in the range of 7 to 10 volt. So the overall power consumption of the CCD sensor will be high. While in case of the CMOS sensor, it requires the single power supply. And not only that, the typical voltage which is required for the CMOS sensor is relatively low, that is 3.3 volt to 5 volt. So overall power consumption of the CMOS sensor will be lesser compared to the CCD sensors. So in the applications where the power consumption is the main criteria, in such scenario, the CMOS sensor is preferred over the CCD sensors. Now let us compare these two sensors in terms of the processing speed. So as I said earlier, in case of the CCD sensor, the charge that is generated in each pixel is converted into the voltage one by one. So overall processing speed of the CCD sensor will be lesser compared to the CMOS sensor. But this processing speed can be further increased by using the multiple shift register. So in this way, by doing the parallel processing, we can increase the processing speed of the CCD sensor. But in this case, we will require the additional amount of hardware. While in case of the CMOS sensor, as we have seen, the charge to voltage conversion is carried out in the same pixel. So processing speed of the CMOS sensor will be higher compared to the CCD sensors. And further, we can increase the speed of this CMOS sensor by using the multiple column select lines. So in this way, by doing the parallel processing, we can further increase the speed of this CMOS sensor. Now let us compare these two sensors in terms of the noise and the sensitivity. So as we have seen in the case of the CMOS sensor, the charge to voltage converter circuit as well as the amplification circuit is integrated in the same pixel. So overall field factor of the CMOS sensor will be less compared to the CCD sensor. And because of that, the sensitivity of the CMOS sensor will be less compared to the CCD sensor. And because of that, dynamic range of the CCD sensor is quite high compared to this CMOS sensor. And not only that, in case of the CMOS sensor, the amplifiers which is being used in each pixel is not identical. So because of that, you will see the non-uniform amplification, and that will act as an additional noise. But now the technology of this CMOS sensor has evolved so much that the noise and the sensitivity of the CMOS sensor is most at par with these CCD sensors. All right, so now let us compare this image sensor in terms of this image distortion. So in case of the CCD sensor, when you expose this sensor for the longer time, then you will see the effect that is known as the blooming. So nowadays, by using this anti-blooming technique, we can reduce this blooming. While in case of the CMOS sensor, the most common type of distortion that is to be known is the rolling shutter. So as we have seen earlier, in the case of the CMOS sensor, the pixels are being read in the line by line fashion. So because of that, whenever any fast moving object is being captured by the CMOS sensor, then this rolling shutter effect is quite noticeable. Like here, as you can see, in the case of this helicopter, the wing of this helicopter is straight, but when it is being captured by this CMOS sensor, then it looks like it is having a curvature. So that effect is known as the rolling shutter effect. While in case of the CCD sensor, all the pixels are getting exposed at the same time. So this effect is not seen in the case of a CCD sensors. So if we want to remove this rolling shutter effect in the CMOS sensors, then all the pixels should be get exposed at the same time, which is known as the global shutter. So nowadays, many of the CMOS sensors are also coming with this global shutter. So as we have seen, when we require the fast processing speed as well as the low power consumption, in such cases, the CMOS sensors are preferred over the CCD sensors. While in applications where you require the high dynamic range and the low amount of noise, like a space application, in such cases, the CCD sensors are preferred over this CMOS sensor. So I hope in this video you understood about the different types of image sensors. So if you have any question or suggestion, please let me know in the comment section below. If you like this video, hit the like.
We will see next video.
Let me tell you about this amazing model. Right now, they have one of their biggest cities in the world. So, अगर आप घर बैठे बोलो and you want to learn something.
हेलो गाइस, कैसे हैं साहब? मैं हूं अली रजा। आज की इस वीडियो में हम देखेंगे व्हाट इज CMOS, कि CMOS क्या होता है और CMOS क्या काम करता है और इसमें जो बैटरी लगी होती है वो क्या काम करती है। तो व्यूअर, वीडियो शुरू करने से पहले जो लोग हमारे चैनल पर नए हैं वो हमारे चैनल को सब्सक्राइब कर दें ताकि आने वाली वीडियोस के नोटिफिकेशन आप लोगों को मिलते रहें। तो वीडियो शुरू करते हैं। हम देखते हैं CMOS क्या होता है। CMOS stand for complementary metal oxide semiconductor। कि CMOS किस चीज का एब्रीवेशन है? ये एब्रीवेशन है complementary metal oxide semiconductor। एक तरह का सेमीकंडक्टर है जो कंप्यूटर्स की इंफॉर्मेशन को स्टोर करता है। ये हम आगे चल के देखते हैं। It stores configuration information of computer। कंप्यूटर की कॉन्फ़िगरेशन इंफॉर्मेशन को स्टोर करता है। कॉन्फ़िगरेशन इंफॉर्मेशन में क्या आ जाएगा? कॉन्फ़िगरेशन इंफॉर्मेशन में कंप्यूटर की बेसिक इंफॉर्मेशन आ जाएगी जिसमें हार्डवेयर और सॉफ्टवेयर के कोलैबोरेशन के किस तरह काम करना है इसकी बेसिक इंफॉर्मेशन को रखता है। द इंफॉर्मेशन इंक्लूड, इसमें इंफॉर्मेशन कौन कौन सी होती है? टाइप ऑफ डिस्क ड्राइवर्स की इंफॉर्मेशन को रखता है, कीबोर्ड एंड मॉनिटर की, करंट डेट एंड टाइम को करेक्ट रखता है, एंड अदर स्टार्टअप इंफॉर्मेशन रिक्वायर्ड ड्यूरिंग बूटिंग प्रोसेस। और दूसरी स्टार्टअप इंफॉर्मेशन को ये होल्ड करके रखता है, स्टोर करता है ड्यूरिंग जो बूटिंग प्रोसेस के दौरान चाहिए होती है। CMOS chip uses battery power to retain information even when the computer is turned off. The information in CMOS can be changed। और जो CMOS चिप होती है वो एक बैटरी को, छोटी सी बैटरी को इस्तेमाल करते हैं कि इंफॉर्मेशन को होल्ड करने के लिए इवन के कंप्यूटर को टर्न ऑफ भी कर दिया जाए तो इसमें जो इंफॉर्मेशन होती है वो पड़ी रहती है, जिसकी वजह से हमारे कंप्यूटर की टाइम और डेट करेक्ट रह पाती है। तो बेसिकली लोग CMOS को, ये छोटे जो बैटरी या सेल होता है इसको लोग CMOS समझते हैं, लेकिन बेसिकली CMOS उसके नीचे एक चिप होती है जो ये सारी इंफॉर्मेशन को होल्ड करके रखती है। द इंफॉर्मेशन इन CMOS कैन बी चेंज, और इसमें जो इंफॉर्मेशन होती है उसको चेंज किया जा सकता है, यानी कि परमानेंटली स्टोर नहीं होती, चेंजेबल होती है। तो उम्मीद है आप लोगों को हमारी ये छोटी सी वीडियो पसंद आई होगी और ये आप लोगों के नॉलेज में इससे इजाफा होगा। तो आप लोग हमारे चैनल को सब्सक्राइब कर।
Okay, this is nothing but complementary metal oxide semiconductor sensors. Now next is line scan. Line scan cameras have a single row of pixels for acquiring data very quickly. These cameras use long and narrow sensors. To generate a 2D image using a line scan camera, the object is made to move along the narrow axis of the sensor, scanning one line at a time and reconstructing the image using the software. Line by line image construction occurs as the item moves past the camera. It is essential to synchronize the timing of the line scan sensor with the movement of the object to obtain stable and meaningful photos. The pixels in these cameras are arranged in a linear fashion that allows for long arrays. These cameras are best employed for high-speed processing like document scanning, print inspection, and detailed inspections demanding measurements in microns. Now we'll see the video what is in by line scan.
When systems work together intelligently across environments,
Next video.
Hi, this video illustrates the capabilities of Iris's frame grabber cards when it comes to synchronizing the camera, sensors, and the lighting control. This video is about acquisition of line scan or 1D cameras. When the object to be inspected is large, moving, or presents itself as an infinite web, it may be suitable to acquire the image line by line using a so-called line scan camera. When using a line scan camera, the frame grabber puts together individual one-line images coming from the camera, builds a 2D image in the host computer memory. As the individual lines of the image are acquired one by one, the challenge is to perfectly synchronize the camera line rate with the movement of the object or the movement of the camera in order to avoid image distortion. This is usually done by using an incremental motion encoder. An incremental motion encoder, either rotary or linear, is able to measure the angle of rotation or the position of an object. An incremental encoder will have its output toggle when the object rotates at a given angle or moves at a given distance. Iris's GrabLink and CoaxLink cards have GPIO input lines dedicated to the connection of motion encoders. They are then able to synchronize the camera line rate of the object to be inspected. When the objects move faster, the acquisition line rate of the camera increases. When the objects slow down, the acquisition line rate of the camera decreases. In the simplest operation mode, the frame grabber will request one line from the camera for each pulse received from the motion encoder. So if, for instance, the motion encoder generates one pulse every 100 microns, we say the encoder pitch is 100 microns. The camera will acquire one line when the object moves 100 microns, while keeping constant resolution. This mode is not very flexible, as you have to change the encoder as soon as you want to adjust the resolution of the acquisition. For that purpose, the Iris's GrabLink and CoaxLink cards incorporate rate converters, a set of devices able to convert the rate or resolution of the encoder. They allow the camera to acquire lines at any programmable resolution, lower or higher than the resolution of the motion encoder. Technically, the rate converter is able to multiply or divide the frequency of the signal coming from the motion encoder. This gives the designer incredible freedom and flexibility during the development of the system. To show you how it works, let's go back to our application where our motion encoder pitch is 100 microns. If we program the rate converter with a 1:2 conversion ratio, it's a division of the encoder's signal frequency by 2, we're going to acquire 2 times less lines, that is 1 line every 200 microns. If we program the rate converter with a 2:1 conversion ratio, It's a multiplication of the encoder signal frequency by 2. You're going to acquire 2 times more lines. That is 1 line every 50 microns. We can even program the rate converter with a 1 to 1.27 conversion ratio. It's a division of the encoder signal frequency by 1.27. We're going to acquire 1 line every 127 microns. With the rate converter, it is now possible to calibrate the system and choose the ratio that gives us perfectly square pixels. In addition, the board is able to decode A/B phase signals coming from quadrature motion encoders in order to know in which direction, forward or backward, the part is moving. When using such an encoder, the card can be instructed to acquire lines only when the object is moving forward or only when the object is moving backward. A feature called backward motion cancellation stops the acquisition when backward motion is detected. The acquisition automatically resumes when motion is again in the forward direction at the exact place where the acquisition was interrupted. Eurosys frame grabbers support continuous web scanning to inspect infinite continuously moving surfaces without losing a single line, and discrete object scanning to acquire the image of objects moving in front of the camera. Let's see how to synchronize the beginning of the acquisition. We will use a trigger that we call start of scan trigger to start the acquisition when the part is in position. Hardware triggers, electrical signals, are connected to the board's GPIO input lines. This can be a presence or proximity detector or a signal from a motion control card. After it is started, the acquisition can continue indefinitely. For example, in this web inspection application where a plastic film is inspected, the inspection virtually never stops. Alternatively, the acquisition can continue for a programmable number of lines. This is used to acquire the image of objects of a known length. Or it continues until an end trigger is received. That's, for example, the case in this postal sorting machine, where the envelopes scanned are of a variable length. If the sensor cannot be put right in front of the camera, an optional trigger delay is available to postpone the beginning of the acquisition for a programmable number of lines. Eurosys frame grabbers include numerous functions that simplify the overall design of vision systems or machines. For more information, please check our website at www.eurosys.com.
Okay, this is nothing but line scan. Next we will see area scan. Line scan means 1D image, area scan means 2D image, always remember. And CCD, that are nothing but 3D images, charge coupled device or digital cameras. Area scan cameras, on the other hand, contain a large matrix of pixels that capture the image data. Imaging sensors in area scan cameras have both length and breadth. In area scan cameras, the imaging lens focuses the object to be imaged onto the sensor, and that image is sampled at the pixel level for reconstruction. Area scan cameras are prevalent in situations where the entire picture is to be collected at once or when synchronizing the movement of the object with the sensors is challenging. Since these cameras operate excellently on discrete components, they are leveraged in a disproportionately large number of uncomplicated machine vision applications. We will see this, then we will see the videos. Now, how to choose a machine vision camera? First criteria is application, that is for machine vision or surveillance. It is known as IP camera, Internet Protocol camera. Then scan type, whether we require area scan or line scan. Second, third, color analysis requirement, whether we want monochromatic light or color. Then camera sensors, whether we want CMOS, complementary metal oxide sensors, or CCD or charge coupled device. Shutter type, global shutter or rolling shutter. Then frame rate, just we have seen rate of frame rate. Resolution you are knowing. Then interface, size, and budget. These are the different criteria to choose the machine vision camera. Now, calibration in machine vision. In machine vision, calibration is the process of mapping the pixel coordinate system of the camera sensor to a world coordinate system. This mapping defines the relationship between a distance measured in pixels in the camera versus the actual distance in inches or millimeters of the object being imaged. The camera sensor is divided into discrete pixels. The image recorded in the vision system Memory is an array recording the amount of charge generated at each sensor pixel location. The convention in machine vision or electronic imaging is to treat the top left corner of the image as the origin and to make all references to the pixel locations in a coordinate system in which X runs across the rows and Y runs down the column of the sensor as shown in the figure. Therefore, this is the calibration. Now this chapter is over. I will show you some videos, then we can stop.
Grammarly does more than catch errors. With Grammarly, you can find
Area scan camera will see now.
this is the first of a series of videos illustrating the capabilities of Eurysys' frame grabber cards when it comes to synchronizing the camera, sensor, and the lighting controller. This video is about acquisition from area scan or 2D cameras. We will distinguish several cases when the object is stationary in the field, or moving, or when the camera is moving, when using strobe lighting or not, or proximity sensors and motion controllers. In all the applications that we illustrate here, the camera acquires a single image every time it receives an electrical trigger signal that we will call camera trigger. The camera trigger is generated by the frame grabber and sent to the camera through the camera link or coax press cable. It is generated in response to a software demand from the application or an electrical signal received on one of the card's GPIO input lines. In this first example, the camera is positioned at successive locations in front of the object. The trigger being a software command coming from the application controlling the motion control card or an electrical trigger signal coming from the motion control card itself. In the second example, the objects to be inspected move on a conveyor belt or on a handler. They stop in front of the camera for the time required to acquire the image under the control of a motion controller card. In this third example, a presence or proximity sensor detects that the objects are in position. The detector also sends an electrical trigger signal to the frame grabber. All these applications cases are supported. The motion controller or detector's electrical output signal is connected to the frame grabber. The frame grabber is able to clean the signal, removing any electrical noise, and provide a reliable event that consistently triggers the image acquisition. If the position of the object in the field of view has to be adjusted, or if the detector has to be placed aside, the frame grabber is able to delay the acquisition for a programmable time period. Using the coax link cards, an incremental motion encoder can also be used together with the I/O toolbox delay tool to delay the acquisition by a configurable amount of encoder ticks corresponding to the position offset of the detector. When using the coax link cards, the detector can be placed several objects in advance. The pipelined architecture of the delay tool ensures that each individual object will be properly shot when it reaches the camera's field of view. Finally, the lighting can also be controlled by the frame grabber. When used, the light will be strobed during the camera exposure time. The duration and position of the strobe pulses are programmable and can be adjusted. Eurysys frame grabbers include numerous functions that simplify the overall.
Okay, this is nothing but area scan, and last we will see that is calibration, and then we will stop.
One of the key problems in computer vision is recovering the three-dimensional structure of a scene from its images. Let's think about this for a second. You have a scene that is defined in some world coordinate frame. And at the end of the day, when you've reconstructed the scene, you would like to know where each point lies in this world coordinate frame, say in millimeters. But what you have at your disposal are images of the scene where points are measured in terms of pixels. So in order to go from images to a full metric reconstruction, you need two things. The first is the position and orientation of the camera with respect to the world coordinate frame. These are referred to as the external parameters of it. And then you want to know how the camera maps via perspective projection points in the world onto its image plane. These are referred to as the internal parameters of the camera, such as its focal length. So determining the external and internal parameters of the camera is what is referred to as camera calibration. So we're going to develop a method for estimating the camera's internal and external parameters.
Before we can do this, we first need a model for the camera. And this is what we refer to as a camera model or a forward imaging model, which takes you from a point in 3D to its projection in pixels. And we would like this camera model to be a linear model. We know that estimating linear models is much easier than estimating nonlinear models. And it turns out that the linear model we come up with is a single matrix called the projection matrix. So now, with the projection matrix in place, we can develop a method for camera calibration. And the way we do this is that we take a single picture of an object of known geometry. And that is all we need to fully calibrate the camera. In other words, to determine the projection matrix in full. What is even more interesting is once we have determined the projection matrix, we can actually tear it apart to figure out both the internal parameters of the camera and the external parameters of the camera. These are called the intrinsic and extrinsic matrices. So at this point, our camera is fully calibrated. And we would like to end with a simple example of how we can use a calibrated camera to reconstruct a three-dimensional scene. For this, we discuss what is called simple stereo. In this case, you have a camera that is in a particular location and a second camera which is displaced in the horizontal direction by some amount. These are identical cameras. We assume that these cameras are calibrated, and using these two views of the scene, we show how we can recover a three-dimensional representation of the scene.
Okay, thank you very much.
Let me tell you about this amazing model.
Thank you very much. Thank you. Now this chapter is completed. Only one chapter is remained. Thank you. We'll stop here. I have taken your attendance. Thank you very much.